The curl of a vector function. From the definition of del, we construct the curl of the vector field V as del cross V equal to determinant x cap, y cap, z cap, dou by dou x, dou by dou y, dou by dou z, Vx, Vy and Vz. When expanded, this will be equal to x hat dou Vz by dou y minus dou Vy by dou z plus y hat dou Vx by dou z minus dou Vz divided by dou x plus z hat dou Vy divided by dou x minus dou Vx divided by dou y. Notice that the curl of a vector function V is like any cross product, a vector. We have seen that the divergence of a vector field is a measure of the tendency of the field to flow away from a point. Likewise, the curl of a vector field is a measure of the field's tendency to circulate about a point. Thus, del cross V is a measure of how much the vector V swirls or circulates around the point in question. Thus, these three functions have zero curl as there are no circulation. In this figure, there are substantial curl as there is circulation. In this figure, there are arrows to the left as well as arrows to the right, suggesting that there is circulation. So this figure is also an example for curl. By convention, a positive curl direction is determined by the right hand rule. If you curl the fingers of your right hand along the circulation, your thumb points in the direction of positive curl. Thus, in these figures, the direction of the curl is along the positive z direction. To check whether a vector field causes circulation, we can perform what is known as a paddle wheel test. Consider the vector fields shown in this figure. Numbers 1 to 7 are indicated at points where we want to check the curl. A simple means to check the curl is to assume the field lines as the flow lines of a liquid and place a paddle wheel at these locations. If there is a circulation, the paddle wheel will start rotating. As we place a paddle wheel at point 1, we can see that the field actually causes rotation of the paddle wheel. Hence, there is a non-zero curl pointing out of this screen. When we place the paddle wheel at point 2, we can see that the circulation is in the clockwise direction. In this case, the curl will be pointed inwards, that is towards the screen. At point 3 also, there is a finite non-zero curl pointing out of this screen. At point 4, you can see that there is a change in strength of the field as indicated by the length of the arrows. Shorter length of the arrow indicates smaller field strength and larger arrow length indicates larger field strength. Hence, when we place a paddle wheel at point 4, it rotates in the anti-clockwise direction. That means that at point 4 also there is a finite non-zero curl. So also at point 5, but when we place the paddle wheel at point 6, we can see that there is no circulation, indicating the curl is 0. This is because at point 6, there is a uniform flow. Now let us place the same paddle field at point 7, where there is a diverging field. In this case, placing the wheel at point 7 would not cause it to rotate as the flow lines are diverging. So in this case, the curl will be equal to 0. As an illustrative example, Let us consider the Ampere's law in electrostatics. If we have a current carrying conductor through which a current density J is flowing, we can see that there will be a circulating magnetic field around any path that bounds that surface. From this observation, Andre-Marie Ampere proposed the circulation of the magnetic field as del cross B equal to mu 0 times J, and this law is known as the Ampere's law. Now let's try to calculate the curl of the following vector function. The curl is defined as del cross V equal to x hat, y hat, z hat, dou by dou x, dou by dou y, and dou by dou z, x square 3xz square minus 2xz. On expanding, this will be equal to x hat 0 minus 6xz plus y hat 0 plus 2z plus z hat 3z square minus 0. This is 6xz x hat plus 2zy hat plus 3z square z hat. There is a finite non-zero curl for the vector function given in the problem. Now let us try to calculate the curl of the following vector function. This will be del cross V x hat, y hat, z hat, dou by dou x, dou by dou y, dou by dou z, y square 2xy plus z square 2y square. On expanding, this will be x hat 2z minus 2z plus y hat 0 minus 0 plus z hat 2y minus 2y, and the curl turns out to be 0.